The San Andreas Fault, the quake that could cut off. Southern California. Southern California depends on imported water, and that dependence crosses the San Andreas Fault. It flows through steel and concrete pipes from the Colorado River and the Sierra Nevada. It crosses hundreds of miles of desert, and to reach the faucets of Los Angeles, those massive aqueducts have to cross the San Andreas Fault. Water is just one component. High-voltage power lines cross the fault. Fiber optic cables cross the fault. Interstate highways and freight rail lines cross the fault. The infrastructure that keeps the second-largest metropolitan economy in the United States functioning is physically draped across a geological fracture loaded with centuries of accumulated strain. The threat is not that the ground will shake and buildings will fall. Engineers know how to build structures that survive vibration. The real threat is severance. When the fault ruptures, the Earth on one side will move northwest. The Earth on the other side will move southeast. They will move simultaneously in opposite directions by as much as 30 feet in a matter of seconds. No pipe, no road, and no cable can stretch 30 feet in an instant. Many of them would fail. This episode follows the physical record of what the San Andreas Fault does to the ground it breaks. It examines the deep trenches that showed how large earthquakes recur on this fault, and it explores what happens when the lifelines of 20 million people are cut at once. There is a narrow, steep-sided valley connecting the Mojave Desert to the Los Angeles Basin. It is called the Cajon Pass. If you drive Interstate 15 toward Las Vegas, you go through it. If you ship freight by rail out of the ports of Long Beach or Los Angeles, the trains go through it. The petroleum pipelines that fuel the Inland Empire are buried beneath it. High-tension power lines carrying electricity from the desert grid are strung above it. Geography dictated this layout. The mountains surrounding Los Angeles form a massive physical wall, and the Cajon Pass is one of the few natural breaks. Planners crowded the region's critical infrastructure into this single corridor because it was the most efficient route. It is also the exact location where two of the most dangerous fault lines in North America collide. The San Andreas Fault runs directly through the pass. It is intersected there by the San Jacinto Fault, a highly active parallel fracture system that cuts southward toward the Mexican border. Geologists refer to the Cajon Pass as an earthquake gate. In tectonic terms, a gate is a complex structural junction that dictates how a rupture behaves. When a major earthquake begins on the San Andreas, the energy travels along the fault line like a wave. When it reaches the Cajon Pass, the geometry of the converging faults acts as a switch. The gate can either stop the rupture, confining the earthquake to a single segment, or the gate can open, allowing the rupture to jump from the San Andreas onto the San Jacinto Fault, magnifying the scale and duration of the event. The physical strain currently locked inside this specific section of rock is immense. Recent geological modeling indicates that the tectonic stress concentrated at the Cajon Pass has reached levels not documented in at least the last 1,000 years. The ground here is not just waiting to shake, it is being pulled in opposing directions by tectonic plates moving at the speed that human fingernails grow, roughly 30 to 50 millimeters a year. Year after year, century after century. That energy is trapped by the friction of the rock. The rock is holding the tension, and all of the infrastructure crammed into the pass is sitting directly on top of the seam. When the friction finally fails, the ground will not simply vibrate, it will permanently offset. If Interstate 15 is displaced by 20 feet, the concrete does not just crack. The northbound lanes end, and the continuation of those lanes sits 20 feet to the right, separated by a newly formed chasm of pulverized earth. A freight train traveling at 60 miles an hour across the pass cannot navigate a rail line that suddenly shifts sideways by the length of a locomotive. The petroleum pipelines will shear. The water mains will sever. The focus of emergency planners is not primarily on the shaking in the Kajun Pass. It is on the physical displacement. You cannot brace a pipe to survive the ground beneath it, moving in two different directions at once. You can only install shut-off valves, plan for the rupture, and calculate how long it will take to rebuild the connections. How scientists estimate the scale of that displacement, and why they expect feet rather than inches, is not based on computer simulations alone. It is based on a physical record left on the surface of the Earth, in a dry riverbed a few hours north of Los Angeles. The fault doesn't store its history in databases. It stores it in the ground itself, in offset channels, sheared sediment, and displaced rock. This channel follows that physical record. If that's the kind of evidence you want to stay with, subscribe. The record continues. In the arid expanse of the Carrizo Plain, about midway between Los Angeles and San Francisco, the San Andreas Fault is not hidden beneath skyscrapers or paved over by freeways. It is exposed. It looks like a long, straight scar dragged across the desert surface. And it is here, at a dry, ephemeral stream called Wallace Creek, that the math of a massive earthquake becomes entirely visible to the naked eye. When water flows down from the Temblor Range during the rare heavy rains, it cuts a channel into the valley floor. The channel flows perpendicular to the fault line. But when you stand at Wallace Creek today and trace the path of the water, something is violently wrong with the geometry. The stream channel hits the fault line, makes a sharp 90-degree turn to the right, runs straight along the fault for over 420 feet, and then makes another sharp 90-degree turn to the left to resume its path downhill. Water does not carve right angles into rock and dirt on its own. The stream did not change its course. The ground changed its location. Over thousands of years, the Pacific Plate, carrying the downstream half of the creek, shifted northwest. The North American Plate, carrying the upstream half, held its relative position. In the 1970s, geologists Kerry C. and Richard Jans began rigorously measuring this displacement. They mapped not just the current channel of Wallace Creek, but older, abandoned channels that had been completely severed by past earthquakes and left stranded hundreds of feet away from the water source. By radiocarbon dating the organic material trapped in those ancient dry channels, the researchers established a precise timeline. They could prove exactly when a specific channel was active and measure exactly how far it had been pushed away by the fault. The arithmetic they uncovered was brutal in its consistency. They found that the long-term slip rate of the fault in this area was roughly 34 millimeters per year. But the ground does not move 34 millimeters smoothly every year. It stays completely locked for over a century, accumulating the tension. Then, in a single catastrophic event, it snaps. By measuring the smaller, more recent offsets along the creek bed, the researchers found that during the last major rupture, the ground shifted approximately 30 feet in a matter of seconds. Wallace Creek is not a theoretical model. It is a physical ledger. The offset channels are the receipts of past violence, proving that the Earth's crust behaves like a loaded spring. The tension builds relentlessly, and the release is sudden, massive, and entirely horizontal. If you want to know what the fault will do to the pipes and highways in the Kajun Pass, you only have to look at what it did to the drainage channels in the Carrizo Plain. But measuring how far the ground moves is only half the equation. The other half is knowing how often it happens. To find that rhythm, scientists had to dig deeper. Before the 1970s, geologists knew the San Andreas Fault was dangerous, but they viewed earthquakes mostly as random, unpredictable events. They had the historical record of a few major tremors, but human history in California is remarkably short. To reconstruct the fault's long-term behavior, someone had to read the geological history. Kerry C. moved his focus southward to a marshy area on the northern edge of the San Gabriel Mountains called Pallet Creek. The location was critical. It sat directly on top of the San Andreas Fault, and because it was a marsh, it regularly accumulated layers of peat and sediment over thousands of years. It was a natural tape recorder. Every time a major earthquake struck, the violent shaking would tear through the marsh. The wet, sandy soil would liquefy. Sand boils would erupt onto the surface. The fault would rip the peat beds apart. Then, the marsh would settle. New vegetation would grow, and a fresh layer of peat would seal the earthquake damage underneath, perfectly preserving it. C brought in heavy machinery and excavated deep trenches straight across the fault zone. He didn't find computer projections. He found the physical cross-sections of disaster. The walls of the trenches revealed a distinct layered cake of sediment, punctuated by violent disruptions. C identified specific layers of peat that had been snapped in half and vertically offset. He found ancient sand blows frozen in the soil strata. By painstakingly extracting organic material from the layers directly above and below each disruption, and testing them with radiocarbon dating, C reconstructed a timeline of destruction that extended back thousands of years. He identified the signatures of at least 12 massive earthquakes at Pallet Creek. The data destroyed the idea that large earthquakes were entirely random. The trenches proved that massive ruptures on this section of the San Andreas occur at somewhat regular intervals, averaging roughly 130 to 150 years apart. This was the birth of modern paleoseismology. C proved that you could read the mud like a barcode. The fault was operating on a geological schedule, driven by the relentless, steady accumulation of tectonic strain. The record at Pallet Creek showed that the system repeatedly locked up, held the tension for over a century, and then shattered. The last time that happened in the region north of Los Angeles, it was one of the largest seismic events in the recorded history of North America, and it happened when the Los Angeles basin was mostly empty. On the morning of January 9, 1857, the tension broke. The rupture began somewhere in the central section of the state, likely near Parkfield, and propagated southward at roughly 2 miles per second. It tore through the Carrizo Plain, past Wallace Creek, through the mountains north of Los Angeles, and finally stopped somewhere near the Kajun Pass. In total, the fault unzipped for over 220 miles. Modern seismologists estimate the magnitude at 7.9. The physical offset at the surface was staggering. In the Carrizo Plain, the ground shifted laterally by nearly 30 feet. Trees were uprooted. The shaking was so violent that the waters of the Kern River were thrown over its banks, leaving the riverbed temporarily dry. In Los Angeles, the Los Angeles River was reportedly thrown out of its channel. It is remembered in historical records as the Fort Tejon earthquake because the military outpost of Fort Tejon suffered some of the most severe structural damage. The adobe buildings were cracked, some roofs collapsed, and 2 people were killed. 2 people. The reason the casualty count was negligible is entirely demographic. In 1857, the city of Los Angeles was a small agricultural settlement with a population of barely 4,000 people. The vast inland valleys and desert margins that border the fault line were effectively empty. There were no massive concrete aqueducts crossing the rupture zone. There were no high-tension power lines, no subterranean fiber optics, and no multi-lane highways stacked with commuters. The earthquake spent its phenomenal energy on dirt, chaparral, and a handful of adobe walls. The physical mechanics of the fault have not changed since 1857. The tectonic plates are still moving at the same speed. The rock is still holding the tension. What has changed is everything we put on top of it. Today, the footprint of the Fort Tejon rupture zone borders a megalopolis. The valleys that were empty are now carpeted with suburban tracts, distribution centers, and industrial parks. But the most critical change is the geography of survival. Southern California outgrew its local water supply decades ago. To sustain a population of 20 million people, the state built one of the most complex water delivery systems on the planet, and they built it right across the fracture. In 2008, the United States Geological Survey published a massive, multidisciplinary study designed to answer a single question. What happens if a magnitude 7.8 earthquake ruptures the southern section of the San Andreas Fault today? They called it the shakeout scenario. It was not a worst-case disaster script. It was a rigorous, physics-based model of a highly probable event, grounded in the paleoseismic data collected from trenches like Pallet Creek. The shakeout model detailed the shaking intensities, the building failures, and the fire risks. But the most chilling section of the report focused on the fault crossing itself, specifically the Tejon Pass and the vital aqueducts. The California Aqueduct, part of the State Water Project, brings water from Northern California down to the south. The Colorado River Aqueduct brings water west from the Arizona border. The Los Angeles Aqueduct brings water south from the Owens Valley. All 3 of these massive pipelines cross the San Andreas Fault. In the shakeout scenario, the fault ruptures through the Tejon Pass, displacing the ground laterally by anywhere from 9 to 15 feet, depending on the specific location. The physics of this are unforgiving. Water pipes are not elastic. When a buried, large-diameter steel or concrete aqueduct is subjected to 15 feet of sudden, horizontal shear, it does not bend, it shatters. The scenario calculates that the major aqueducts crossing the fault would be completely severed. The immediate result is not just a loss of pressure. It is the sudden, explosive release of millions of gallons of water into the surrounding terrain, washing out access roads and triggering localized landslides exactly where repair crews need to go. The state of California relies on reservoirs south of the fault to hold emergency reserves, precisely because they know the aqueducts will fail. But reservoirs have limits. The shakeout report estimates that it could take up to 6 months to fully repair the main water delivery systems crossing the fault line. 6 months, and the water is just the beginning. The same displacement that severs the aqueducts severs the high-pressure natural gas lines. It drops the high-voltage transmission towers that carry electricity from the desert into the basin. When a transmission tower is subjected to intense ground acceleration and physical displacement, the tension on the cables can snap the steel structures like twigs, causing a cascading failure of the local grid. The scenario maps a sequence of disconnection. The highways are impassable. The rail lines are twisted steel. the water is cut. The power is severed. The telecommunications lines running alongside the rails are torn apart. This is what geologists mean when they say the real threat is severance. The earthquake acts as a physical blade, dropping a guillotine on the umbilical cords of Southern California. The only reason this has not happened yet is that the southern section of the fault is currently in a state of deep, unnatural silence. The San Andreas Fault is roughly 800 miles long. It does not break all at once. It breaks in segments. In 1906, the northern segment ruptured, destroying San Francisco and shifting the ground by nearly 20 feet. In 1857, the central segment ruptured in the Fort Tejon earthquake, shifting the ground in the Carrizo Plain by 30 feet. But if you move further south, past Los Angeles, past the Cajon Pass, down through the Coachella Valley, and toward the Salton Sea, the historical record goes dark. The southernmost section of the San Andreas Fault has not ruptured in recorded human history. The last time this segment unleashed a major earthquake, European explorers had not yet mapped the California coast. Through paleoseismology, digging trenches like the ones at Pallet Creek, but further south, geologists have dated the last major rupture on the Coachella segment to approximately the year 1680 or 1700. That means the southern fault has been locked and accumulating strain for over 300 years. Based on the long-term slip rate of the tectonic plates, roughly 1.5 inches per year, the fault should break, on average, every 150 to 200 years. The Coachella segment has missed at least one, and possibly two, of its expected rupture cycles. Geophysicists call this a stress deficit. The Pacific Plate did not stop moving in 1700. It has continued to grind northwest, year after year, millimeter by millimeter. The deep crust beneath the fault is continuously creeping, but the upper crust, the brittle rock at the surface where we live, is locked by friction. Imagine stretching a heavy rubber band for 3 straight centuries. The deficit is not theoretical. It is physical displacement that has been forced into the deep rock, waiting for the friction at the surface to fail. Scientists calculate that there is currently enough pent-up strain in the southernmost section of the fault to power a magnitude 7.8 or greater earthquake. This is the scenario the shakeout report modeled. A rupture that begins in the deep south, near the Salton Sea, unzips northward through the Coachella Valley and slams straight into the Cajon Pass bottleneck. At the scale of plate tectonics, the strain does not accumulate forever. The physics do not allow a fault to absorb stress indefinitely. The rock has a breaking point. The silence on the southern San Andreas is not a sign of stability. It is the sound of a system that has been loaded to absolute capacity. In Los Angeles, the threat of the San Andreas Fault is often treated as a cultural background noise, a plot device for movies, a punchline about falling into the ocean. But the reality is infinitely more precise and far less theatrical. The fault does not open up to swallow cities. It does not break the continent in half. What it does is far more surgical. It shifts the ground horizontally, instantly breaking every rigid connection built across it. We have built a civilization that assumes the ground is a static foundation. We poured concrete, laid steel pipelines, and strung high-voltage wires under the assumption that the coordinates of the Earth yesterday will be the coordinates of the Earth tomorrow. Wallace Creek proves that assumption is false. The trenches at Pallet Creek show that major disruption on this fault recurs over long intervals, and the stress deficit in the Coachella Valley shows how much strain has been building on the southern segment. The The tension in the rock is a physical debt, and that strain is eventually released. When the friction finally fails, the rupture will not care about the ingenuity of the California aqueduct. It will not care about the traffic volume in the Cajon Pass or the economic output of the Los Angeles Basin. It will simply follow the mechanics of releasing 300 years of accumulated strain. The ground on one side will move northwest. The ground on the other side will move southeast. And in that fraction of a minute, the lifelines that took a century to build, the veins and arteries that keep 20 million people alive in a semi-arid desert, will be violently, physically severed. The system does not pause for readiness. It releases when friction fails,